Welcome to Study Loop.
Hi everyone, thanks for joining me today. So what we're going to be looking at is a problem dealing with power. So what we have in the first case is a biker going up a 3% slope, and the biker is going at a velocity of v equal to 5 feet per second. The biker and the bike have a mass or a weight equal to 135 pounds, and they're going up a 3% slope. In situation 2, we have another biker going down that same 3% slope at a velocity v. That v is equal to 20 feet per second, and they have a total mass or weight of 198 pounds. What we're asked to solve for is the power that is applied by the biker in situation 1 and the power that's dissipated in situation 2 by the brakes. So to find the power developed by the biker in situation 1, we draw a free body diagram, and what we have is we have the biker, we have the normal force from the ground, we have the force applied by the biker, and then we have the weight force that is due to gravity. And what we're going to see is we're also going to come up with our convention for our direction. So that's positive x, and this is positive y. And as we see that when we resolve our forces, that the force of the biker is actually overcoming the force of w sine theta, and theta is the angle between the horizon and the slope itself. Remember that we're given that the slope is a 3% slope. So that means that we can solve for theta by saying that tan of theta equals 3 over 100. And this gives us a theta equal to 1.72 degrees. So as I said before, the w sine theta is that component that is being overcome by the biker. So we can go ahead and say that. Now this is simple. We know that power is equal to the force of the biker times the velocity. We know that the force of the biker is going to be mg sine theta, and the velocity is given to us as 5 feet per second. So since we already know these variables, we can go ahead and plug these in, and we get a power developed by the biker as 20.25 foot-pound per second. That is our final answer. Now let's go over to situation 2, where we're actually trying to find the power that is dissipated by the brakes. So again, we're also going to draw a free body diagram shown here. Have that same normal force going up from the ground. We have a weight force, and now we have the brake force acting in the opposite direction of motion. We're going to go ahead and draw a coordinate system. These are the positive directions. And similarly as before, here is an angle theta. That is the same theta as before because we're also looking at a 3% slope. And we'll see from breaking down the weight force that the force of the brake is counteracting w sine theta. So just to write that down, we see that F brake is equal to w sine theta. As before, power is going to be equal to the force of the brake times the velocity. Now, we know force of the brake is w sine theta, so we can just go ahead and write that as mg sine theta times the velocity, which is given to us as 20 feet per second. We know the mass, or the weight, to be 198 pounds. So this is known, this is known, this is known. We can plug it in, and we see that the power that is dissipated by the brakes is 118.75 foot-pound per second. Thank you. And that is our final answer.